The title of this talk is Thinking, Seeing, and Consciousness, and the idea of it is that the key to understanding consciousness is the distinction between perception and cognition. So I think there's a joint in nature between perception and cognition that's symbolized by this barbed wire fence. Can you see the pointer? Is that visible? Okay. So it's complicated because although no perceptions are cognitions, no states are both perceptions and cognitions, cognition can use perceptual simulations in cognition, in thinking, reasoning, etc. So the conclusion I'm going to be arguing for is that conscious perception, which is this shaded area, need not involve cognition or conceptualized states. So cognitive and conceptual theories of consciousness, of conscious perception are wrong, and I think therefore cognitive and conceptual theories of consciousness per se are wrong. So, and since I think this is a significant conclusion because a lot of people, probably a lot of people here, are inclined towards cognitive or conceptual theories of consciousness. So my argument depends on the idea that perception is iconic in format, non-conceptual and non-propositional in content, and I think there's some other properties that probably aren't essential, something to do with the cognitive architecture, the sort of quasi-modularity, although it's only quasi, perceptual constancies. But the basic idea is that perception is constitutively iconic, non-conceptual, non-propositional, whereas cognition does not have those properties constitutively. So I think this is a core characterization of the natural kind perception that's enough to distinguish it from cognition. Let me say a little bit about terminology. So the format of a representation is the structure of a representational vehicle. The content is the way the representation represents the world to be. There can be one format, two contents. So a standard example is the sound of you make when you say Oedipus leaped. This is from Davidson. Can express one content in English, another content in German. The content that kitten or cute can be expressed in two different languages, which I got off of Google Translate. So another item of terminology is, what do I mean by cognition? The paradigms of cognition are thinking, reasoning, deciding, planning, evaluating, formulating a report, long-term memory. They're all propositional and conceptual entities or processes. Those are the paradigms. I think it may be possible that there are other kinds of cognition that are not paradigmatic cases of cognition that might involve fragments of propositions, but I'm not going to go into that. What do I mean by concept? Okay, so the word concept is famously ambiguous. It's often been used in the history of philosophy as a kind of a word for meaning. And we express this when we say these words all express roughly the same concept. Whereas there's a representational sense, which is the one I'm going to be using, in which different concepts of dog can have different causal roles. That's my sense. So in my sense of concept, actually in both senses of the concepts, Oedipus can have two concepts of Jocasta. A concept involves a way of thinking about what it's a concept of. Okay, so I'm going to move now from terminology to substance, and I think I can give you the idea of what I'm trying to do by the example of the wasp. Okay, the wasp is a great candidate for non-conceptual and non-cognitive and non-conscious perception. That is just this. Okay, so what's the argument for this? Well, I rely on Peter Godfrey Smith, who in a number of publications has made some very cool points about wasps. First of all, just to get the facts on the ground, they have fantastic vision. That's their main sensory modality. They use their vision to track and ambush prey. They pick out what creatures are their prey. They have all the perceptual constancies, size constancy, shape constancy, etc. Second, there's a lot of evolutionary pressure to reduce brain size for flight. They need to be light because they require great agility in the air. It may be that some earlier evolutionary antecedents of wasps had perhaps some cognition, but there's reason to think that wasps don't, and partly is maybe due to the fact that they had to get rid of excess weight for things they don't need. Okay, so here's what's relevant to consciousness. Wasps have no wound tending. That is a technical term that refers to the fact that when an animal damages part of its body, it favors that part of its body. So a leg is damaged, the animal doesn't try to walk on the leg. The animal takes care not to damage it further. But not wasps. You cut off a piece of the wasp, and if it can move, it will just go ahead and do whatever it was trying to do before. It pays no attention to damaged parts of its body. No wound tending, suggesting it does not feel pain. It shows no indication of anything you might call pain behavior. Now onto cognition. The wasps have short lifespans, so they have little use for learning. They are capable of Pavlovian conditioning, the kind where the dog salivates in response to the light that accompanied food. But they have not been shown to be capable of a more sophisticated kind of conditioning called instrumental conditioning. And that's when you make a voluntary response that is positively reinforced or negatively reinforced. If it's positively reinforced, you're more likely to voluntarily make that response. If it's negatively reinforced, you're much more likely to not make that voluntary response. Wasps have not been shown to be capable of that. And famously, they have stereotyped action patterns. And here is a famous passage, which I won't read, from this book by Dean Wooldridge. But the point of the passage, which I've highlighted in yellow, is that wasps have certain action patterns that they do. And if you disrupt one of those action patterns, they just start over again. And in many cases, they have been seen to repeat the same stereotyped action many times, including Wooldridge reports one point it was observed that the wasp repeated the same thing 40 times. Okay, so they are a really good candidate for non-thinking zombie killer robots. All right, so that gives you an idea of what pure perception, uncontaminated by consciousness or cognition, might be. Just think the wasp. Okay, let me switch gears now and talk about the issue I'm trying to raise in terms of the way things look. So here are a lot of ways things look. Something can look blue, look like a lot of dots, look like a face, look expensive, look like a piano. But these, we say looks. The question is, how many of these are really perceptual? Now, as opposed to perceptual judgment. So I'm going to be relying on the distinction between perception and perceptual judgment, which I will explain in a minute. Actually, you know what? I should probably explain that right away. So, yeah, so I'm going to try to make you subjects in an experiment, which may not work so well, but because of the screen. But you're going to see some things. Just pay attention. Okay, how many saw a 6? And what was that? What was the suit of that 6? I got one. How many hearts? Anything else? Somebody thought it was a red spade. How many people thought that? Okay. All right. So what was on the screen, you've just been a subject in a famous experiment from the 1940s, the Brunner-Postman experiment. And what was on the screen was actually a red six of spades. Many people report six of hearts. They say the perceptual experience was the six of hearts. Other people report the perceptual experience was the red six of spades. And now the issue comes up. Is it possible that everybody experienced the red six of spades, and that those who reported six of hearts really were reporting a conceptual overlay on that perceptual experience? It was a matter of perceptual judgment rather than perception. And here's the thing. You can't really rely on introspection to tell the difference between these, because those who reported the six of hearts may have consciously seen the red six of spades, categorized it as a six of hearts with a conceptual category, and then formed a mental image of the six of hearts. And so when you get that report, you don't know which it is. Now, fortunately, there are empirical methods that can get to some distance in separating these things, and that's really what I'm going to be talking about. I think in many cases, what people report is actually a post-perceptual judgment. And I think in the case of these things, I believe that when somebody says something looks expensive, I believe they are reporting a post-perceptual judgment. Likewise for piano. In the case of looking blue, looking like a lot, and looking like a face, I think those are all perceptual. I think looking blue is a low-level perceptual property. I won't go into the distinction between these distinctions between levels. Okay. Now what I'm going to do is I am going to try to give you a sense of how you can tell the difference between perception and post-perceptual judgment, more generally between perception and cognition. And I'm going to start with these basic perceptual phenomena. So one that is very widely used in vision science is something known to Aristotle, and here's an example of it. So I need you to look at that cross. Now, I'm sorry this may not work. Just fix your eyes on that cross. Don't move your eyes. Okay? And we need about 30 seconds of this. We may need more because of the washed out quality of the picture. So I'll wait another 10 seconds, but keep your eyes on that cross. And then I'm going to switch to something else, and I want you to pay careful attention to what you see. Anybody want to say what you saw? Did anybody get it, look colored and then it wasn't colored? How many got that? Oh, good. Okay, in a room with proper projection, everybody gets it, okay? So what happened was, the first picture manipulated your opponent process system. For example, there's a yellow-blue channel, and you as people say, fatigued the yellow side of the yellow-blue channel, so then when you saw this, it looked blue or blue-green, okay? So that gives you an example of how perceptual adaptation can be used to explore what is perceptual and what isn't. And going back to that, this picture, yes. So what you would want to know about whether something can really look expensive in the sense of be perceived to be expensive is whether you get adaptation to the property of looking expensive over and above the color, shape, texture, etc., low-level properties. So that is the name of the game in distinguishing perception from cognition. So I think, just to be clear, adaptation is necessary for perception, but it's not sufficient because some cognitive states involve perceptual simulations, imagery, mental maps, various other ones. Adaptation is sufficient for perception or perceptual materials. Is adaptation only? Well, I've just covered this, actually. So let me move to another visual phenomena, pop-out. You find it very easy to pick the red dot here, but not here. And here's a little graph. When there's a lot of dissimilarity, when the target and distractors are very dissimilar, the set size doesn't matter very much. But notice that similarity or dissimilarity is a matter of visual similarity. And so that introduces a certain circularity, because you can only specify vision by appeal to other visual properties. And the way to avoid the circularity is to find a bunch of methods that isolate the obvious cases of perception on one side and the obvious cases of non-perception on the other. And in fact, we have a lot of such methods, and I'm going through a few of them. Incidentally, these curves are for pigeons, okay, which is, again, one indication that there's not a lot of cognition involved in it. There's also pop-out for other high-level properties. Is there one figure here that pops out? What? Face, okay. Another mechanism that isolates perception is interpolation. So you see a triangle there, even though there's no triangle. You see the lines of the triangle. And this occurs in a lot of lower animals that perceive. And here are a number of properties that I won't go into that cluster together, that isolate the same ideas. And the key thing here is they group together, and that gets rid of the circularity problem. Okay, methods of distinguishing cognition from perception. I'll just go very quickly through one extremely simple method that can be used. And I'll pay attention to something that you may have heard of. This is an experiment by Keith Payne. So the subjects see a black face or a white face. They then see a gun or a tool like a wrench. And then there's a brief mask to keep an image from reverberating in the early visual cortex. And the result, which you probably have heard of, is that when they see a black face, they're biased in the direction of calling this saying this is a weapon. They see a white face, they're biased in the direction of saying it's a tool in the U.S. Here's an interesting experiment done by Payne. He presented these objects making them very hard to see, and he asked the subjects to give their answers to whether it was a gun or a tool or a weapon. And he asked them then to say, give one of three responses: see, know, or guess. See meant they were confident in the answer and have perceptual detail. Examples that he gave them were things like, if it's a gun, the color of the stock or the shape of the barrel. The second response is no. They know the response is correct, but no perceptual detail. And the third is guessing. And here's the interesting result, is that stereotype congruent, that is, the biased responses, were more than the incongruent, unbiased responses, only in the case of the no response, not in the guess or the see, suggesting that this is an effect on perceptual judgment, not on perception, because the cases in which they were biased are cases in which they could not report the color of the barrel or the shape of the color of the stock, the shape of the barrel. That's just one indication of how you can get an experimental handle on this. Okay, let me now move, because I don't have much time, to the case that perception is non-propositional. And I'll just mention these properties of perception. They're not conclusive, and I have more to say on it, but here it is. You cannot see something as if red, then blue. You can see something as non-blue by seeing it as red, but you cannot see something simply as not blue. There's no negation in the perceptual system. And we can argue about this, but I'm just stating what I think to be true. One can see something as intermediate or indeterminate between red and blue, but not as having the disjunctive property of simply being red or simply being blue. And then likewise for conjunction, which is a bit more of a complicated case, various kinds of quantification, perceptions just don't seem to have logical properties, suggesting that they are not propositional representations. This goes against the dominant view in philosophy that perceptual states are propositional states. But I think that people really have not examined this properly. Okay, perception is constitutively non-conceptual. So there's different ideas of what non-conceptual content or states are floating around. I'm just going to give a very simple, two simple cases where creatures can have perceptions without the relevant concepts. I've already mentioned one where, I didn't give a very strong evidence, but there's some evidence in the case of wasps. Now what I'm going to do is quickly move to human infants. And one reason for this is that, well, the main reason is there's terrific data on the non-conceptual color perception of human infants. So the data depends on this phenomenon known as categorical perception. So as you probably know, in the case of a rainbow is a continuous band of wavelengths, but we see it as digitized into bands of color, right? So there they are, digitized into bands of color. You can use this categorical perception. So first of all, the signature of categorical perception is faster and more accurate discrimination across categories than within a single category. Okay? So if you're across a category boundary, you find it very easy to tell the difference. And so here's the empirical claim. Infants show categorical perception of color before they have conceptual abilities involving color. So I'm going to rely on the work of Anna Franklin, who's a psychologist at the University of Sussex. So one method that she uses, very simple method, is you show them a screen that's a uniform color except for a disk of another color. If the baby sees that color as different, the baby is likely to saccade, which means move your eyes in a ballistic motion to that thing. Everybody get that? Okay. And you do it quicker if they're from different color categories. So you can use that to judge the baby's color categories. The basic result, just the first result, is that in 4 to 6 month old human infants have almost adult level color perception. That's the ground floor result. They do this as well as, almost as well, this kind of thing almost as well as adults by the time they are around 4 to 6 months. Here's another technique that can be used. This is called habituation. It's not adaptation. It's a completely different phenomenon from adaptation. The way it works is this. You have two sides to your screen, and you show something again and again and again. The thing goes on the screen. The baby, it appears the baby is likely to look at it. But if you keep repeating the same thing, the baby gets bored and stops looking at the screen. The baby will look at its feet instead of the screen. Okay? Then, if you introduce something different, there is a recovery of interest. The baby will look longer. And they have cameras that above the stimulus that look at where the baby's eyes are, and they're blind coded by coders who don't know what's on the screen. And they measure the looking time. So, and this looking time the recovery of interest can gauge whether they see it as different and whether they see it as a different category. You get more recovery of interest if it's of a different category. And you can use this to map out baby color categories. And here they are. This is a partial representation of baby color categories. The lines, the double lines, represent things that are very closely associated in the same category. The gaps are the category boundaries for human infants in all cultures. And here is a little, this is infant. I don't know if you can read this. These discs are the infant color boundaries. There are 4 color boundaries for infant color perception. These are data on 4 different language groups, or 3 different language groups and something else. So in the English speakers match infants in 3. That stars mean a match with the infant color categories. We lack a color category where the infants have them. In this case, we don't, in English, we don't have a color I have no idea what it is in Polish, but in English we don't see a color boundary between, I don't know, sort of greenish brown and brownish green. Okay, so here is the interesting thing, is that infants' color categories are not just immature versions of adult color categories. And the way you can tell this is this. The signature of, as I mentioned, is faster and more accurate discrimination between categories. That's these hatched lines. This is time it takes to initiate a switch, a looking time measure. Infants show categorical. This is the signature of categorical perception. The lower hatched than the gray. I don't know if can you see the hatch marks on the screen there? Okay, so infants have categorical perception on the left side of the screen, not on the right side. There's no significant difference on the right side. Everybody understand that? In the case of adults, we have more significant categorical perception on the right side. And those who know anything about the brain know that what's the difference here is that the left visual field is controlled by the right hemisphere. The right visual field is controlled by the left hemisphere, so adult color perception is largely linguistically conditioned. This is where the concepts are in the language hemisphere. So what adults have done is they've imposed a language conceptual color category onto a non-conceptual color categories in the case of infants. We still have the non-conceptual color categories here in the right hemisphere, left visual field, but we've superimposed category concepts on it. So here is the argument. 4 to 6 month olds have color perception without showing any abilities diagnostic of color conception, whereas 4 to 6 month old infants do show concepts of shape, size, and kind. So here is a graphical representation. We have the babies who have, and this is genuinely a 4-month-old baby, who have near adult levels of color perception. We've got the 12 months old who have the beginnings of color concepts. And then this intermediate period, they have color perception without any color concepts. And this is very significant because to the extent that the evidence is good, it shows that perception does not require concepts. And I think the evidence is strong that it's conscious perception. And so that shows that cognitive and conceptualist theories of consciousness are wrong, contradicting a very widespread view in all over fields that talk about this. So that's the outline. So I don't have much time, so I'm going to go through this very quickly. In fact, I think I'll skip quite a lot here. So here is one item of evidence that children do not have color concepts in the ages that I'm talking about, and that's this. The child is in front of a screen. Something of one color goes out one side, something of another color goes out the other side. The screen goes down, and then the question is, does the baby expect two things? And the answer is lower than 12 months, they do not expect two things, okay? They do not see the color difference they cannot reason with color. They don't use the difference in color to reason, to form an expectation that there are two things behind the screen. But they do, if they're different shape or kind information, they do expect two things. Okay? That suggests color experience can be non-conceptual. Here's another different experiment. You have one shape come out and go back, another shape goes out and goes back, and then the screen goes up. And if you have both of those shapes, that's expected. If you don't have both of those shapes, it's unexpected. Now, it works for shape at 12 months old, but not for color. Okay? They can see a red thing go out and go back. Well, I guess for color it's really the same. It's pretty much the same as the one. Yeah, okay, so maybe it's not that different. Here is a different one. Okay, so if you have two things of the same shape on the two sides of the screen, something interesting happens. A frog goes on the screen on one side and does a lot of dance and there's music. And the babies like that. They pick things the babies like. And there's a rule, same shape, wonderful object on the left or on the right. And the babies can learn that rule for shape, but not for color. So the 12-month-olds could learn the rule, same shape, predict something interesting. Okay, those are 12 months. Now here is further information on this. 2 years, 3 months later, many children do not know the basic, the four basic color words. So Mabel Rice in 1980 did a teaching experiment in which children who did not know the color words were taught the difference between red and green. For most children, learning this took over 1,000 trials. Here's an observation that many parents have made. This is Charles Darwin. I won't read the whole thing. But what he's saying is he thought his children were colorblind because they couldn't learn the color words, even though they learned all kinds of other words. So here's a summary. I'm sorry I'm going very fast here, but I want to finish in time to have some question period. Okay, so infants can see colors at the adult levels at 4 to 6 months. They perceptually categorize color. They can use shape, size, and kind information in forming expectation and as inputs to rules at least 6 months earlier than they can use color information. 2 years later, most children do not know the basic color words, and many children don't seem to know what adults are talking about when they talk about color. If you have a young child, try it yourself. You'll see. Substantial reasoning with color seems to happen at the same time as learning color words, and that's when they're getting the color concepts. So I take this as strong evidence that 6 to 11-month-old infants have color perception, including conscious color perception without color concepts. And now, I think all perception is non-conceptual, but so far this is really just a burden of proof argument. And this justifies the non-conceptual. I already justified the non-propositional. Okay, let me now move to the conclusion in terms of consciousness. So what about these conceptualist and cognitive theories of consciousness? So I think they're wrong. First of all, let me say what they are. Okay, so the most well-known, I think, cognitive conceptualist theory of consciousness is the higher order thought theory of consciousness. So what is it to have a conscious pain? It's to have a pain that is accompanied by a thought to the effect that one has a pain. Okay, what makes a pain conscious more generally is that there's another state, a cognitive state, which is about the pain. That's the higher order. I mean, some people have different higher order theories. This is the higher order thought theory, but all the higher order theories involve concepts, cognitive states with concepts of the state that is conscious. So they require a concept of the conscious state, And if the higher order thought theory is right, the children who have color perception without color concepts could only have unconscious color perception. And I take that to be a reductio. Now, what's the reason for thinking the kids do have conscious color perception? Well, first of all, they're conscious creatures. But secondly, they get bored seeing the same colors again and again. They look at their feet. They regain interest when the colors change. A second point is what sometimes is called the oddball effect, is that if you put a EEG helmet on a child and you have same color, same color, same color, same color, and then a different color, you get a marked indication of the color change all over the child's cortex. Another point is the one I made earlier about the children, okay, that they scan to the, they move their eyes, they saccade. Okay, why do they do that? That's because they have conscious perception of color difference. So I take these to be, look, in the case of consciousness, there is, in the absence of a real science of consciousness, we don't have any conclusive argument for consciousness anywhere. I don't have any conclusive argument that any of you are conscious. And I see a few people who might not be. You can't get conclusive arguments. What you get is evidence, and I think this is evidence. Now, just to be clear about whether the higher order theory really is a conceptualist theory, there is a famous problem first mentioned by Karen Neander, which is, what do the higher order views say about when the higher order state is I'm having a sensation of red, but the first order states are either some other color or no color at all. So what do they say about this? It's a problem for them. Is the conscious experience determined by the first order state or the conceptualization of them? And the answer is, well, it has to be. If the first order state is dominant, then why not just have a first order theory? If you're going to have a higher order theory, it seems like you have to say that the higher order state is dominant so that you can have a conscious experience of the sensation of red even when you're having a first order sensation of blue or of nothing. And David Rosenthal has embraced this. He's one of the proponents of the higher order view. He says, if one has a sensation of red and a distinct higher order thought that one has a sensation of green, then the sensation of red may nonetheless be detectable by various priming effects. I won't go into what that is. But what it will be like for one, that is what it's the conscious experience, what it's like to experience it, is that one has a sensation of green. So that's the claim. So I take this to be a reductio of the view. Now, in the few minutes that I have left, let me move to a different theory. This is a theory very common among cognitive scientists, the global neuronal workspace theory. And it was first suggested by Bernard Bars, but has been really very well developed by two French researchers, Stanislas Dehaene and Jean-Pierre Changeux, and other colleagues. And I won't go into the full idea. This is a diagram, but I won't go into the full idea. But the main idea is that there's central cognition localized in the frontal lobes of the brain, and that what it is for a perception to be conscious is for it to trigger ignition. These are perceptual states in the back of the head. The filled circles and links are active. The circles are active. The circles are nodes. The links are links between nodes. And the idea is that some of them are activated, but they never make it into the global workspace. Others form a dominant coalition. These are basically neural networks, which involve both the front of the head, the cognitive states in the front of the head, and perceptual states in the back of the head. And the idea is that the leading intuition behind it is that when you are conscious of something, you can use it in evaluation, verbal report, planning, and long-term memory cognitive and conceptual capacities. The idea is that when something is conscious without further processing, it is available to cognitive processes. And that is the problem. The problem is that evaluating, reporting, planning, coding, and long-term memory require concepts of the coded items. So this is, at least in the dominant versions, a cognitive and conceptualist theory of consciousness. And so it's wrong. So there we are. The idea is that there's a fundamental border between perception and cognition, and the nature of that border shows that cognitivist and conceptualist theories of perception are wrong.